my name is Evan Donahue. I'm currently a researcher at the University of Tokyo, and I'm going to talk today about guarded fresh goals, which are a form I added to a Smalltalk implementation of miniKanren to make explicit some of the dependencies between relations and use those dependencies to prioritize the search. I'd like to start by defining what guarded fresh goals are and describing what purpose they serve, and I'd like to talk about how they actually work and use that to speculate about some of the performance results that arose during the evaluation. Finally, I'd like to sketch out why this work was undertaken and what kinds of work I'm hoping it will enable in the future. So to start with, what do I mean by guarded fresh? Let's first consider a common pattern in miniKanren programming for destructuring a list term. Some cons pair q is passed into some relation. We create two new variables, a and d, for the car encoder of q, and we unify their pair with q. We then go on to write additional goals that use a and d. We need this pattern anytime we want to access the contents of a complex term. Guarded fresh, syntactically, is just a slightly simplified way to express the idea of destructuring a complex list term to access its contents. It consists of two parts: a set of binding forms that pair variables with patterns, similar to pattern matching forms in other languages. In this case, the form expresses that q is to be unified with a pattern consisting of a pair a and d, where capitalized symbols in the pattern are to be replaced with fresh logic variables. After the binding forms, we just have body expressions that use the new logic variables a and d, similarly to the way that fresh normally works. Of course, this is not a talk about syntactic affordances primarily. What is important about this form is that it supplies the implementation with two pieces of information. First, that the subgoals of this guarded fresh goal depend on q. And second, that q is a complex term that may contain unbound logic variables. The key here is that before we evaluate these subgoals, we'd like to know as much as possible about the constraints on a and d, and after we evaluate these subgoals, we'd like to be on the lookout for any further constraint information pertaining to a and d so that we can as quickly as possible prevent them from becoming committed to unifications that will ultimately fail after a long and expensive search. We'd therefore like to gather as much information about q as possible before executing those subgoals, and prioritize goals pertaining to q after we've committed to creating fresh logic variables for its contents. I should note that in terms of capturing these dependencies, the guarded fresh form itself is probably immaterial. In an appropriate language and context, I would expect this to be possible with static analysis as well, as I know similar things are done in other recent work. What the guarded fresh form itself accomplishes, really, if anything, syntactically, is just a bit of social engineering. By giving the programmer a simpler form dedicated to expressing common idiom, it encourages the programmer to annotate the program with that dependency information. In the embedded context in Smalltalk, syntactic analysis would be possible, but would probably require a much greater separation between the host language and the embedded miniKanren operators due to the liveness of the image. A new form, by contrast, was no more difficult to implement than any other form in the language. Now, the reason we want to track this dependency information is that it can let us prioritize the search behavior in ways that are difficult to achieve through more general optimization strategies or through manual optimization. The inspiration for this work comes largely from work on guarded horn clauses for parallelism and prologue, hence the name. Although guarded horn clauses were primarily a construct motivated by parallel processing, it was also observed that the types of search rearrangement they permitted had other uses. This is a slightly simplified example from a 1985 paper by Ueda. The prologue rule consume destructures a buffer shared between two parallel processes and checks whether the next element is an end of stream or EOS symbol. If the next symbol is EOS, we're done. If it's not EOS, we recursively consume the tail of the buffer. And I've removed the code here that actually processes the head elements. This is purely just consuming elements from the buffer and throwing them away. In between the head clause on the left and the body clause to the right of the vertical bar, we see the guard. The purpose of the guard is to determine whether the rule should execute or whether it should be suspended to execute at some point in the future. If H is bound, then the disequality will either succeed or fail. If it is free, however, the rule will suspend and await the binding of that variable. The effect is to sequence the logic of the buffer so that the results can only be consumed after they are produced. Independent of its implications for parallelism, consider the comparable miniKanren code. The relation accepts a buffer variable, it destructures the head and the tail, and then it makes a choice. If the head is bound to EOS, do nothing, otherwise consume more of the buffer. Suppose that in the code in which this is used, consume is called before the relation that produces the elements in the buffer. Running fully relationally, the consume relation is going to produce a one-length buffer with an EOS, a two-length buffer ending with an EOS, etc. Each of these buffers is going to get sent to the producer, which will fail unless it tries to produce exactly that many elements. If producing those elements is expensive, this ordering will make it many times more expensive. Even outside of imagining that two parallel processes are communicating through this buffer, if the buffer is shared between two single-threaded relations and the miniKanren engine needs to allot its search time to those relations, the whole program is going to be incredibly slow. In this case, it's easy enough for the programmer to order the relations appropriately to match the expected use. However, in many practical cases, the order is dynamic and cannot be optimized by the programmer ahead of time. One case, and the motivating example in this talk, is relational program synthesis. Guarded Fresh is not exclusively for program synthesis, but synthesis does exhibit a form of this same producer-consumer architecture if you squint at it a bit. I know many will be already familiar with program synthesis in miniKanren, but for those who are not, a simple approach to synthesizing, for instance, scheme programs in miniKanren is to write an eval relation that mirrors scheme's eval function. If an expression is supplied as the first argument, the relation will evaluate it normally. If, however, the first argument is free and inputs are supplied through the environment and some desired outputs are supplied in the value argument of the relation, it will synthesize a program that accepts the input arguments and produces the desired values. Now, even without any extra work, miniKanren is going to be a bit smarter than just generating random scheme programs and testing them. Because we have these ground inputs and outputs threading through the interpreter, we're going to be able to say, for instance, that if the output of the program as a whole, or even any sub-expression, needs to be a Boolean based on the output value, we're not going to be able to synthesize that with a cons, no matter what arguments we pick. So we can just cut that whole branch off. This dynamic is important because it's what we want to take even further with the information we get from the guard clauses. Many interesting programs are going to require more than a single input-output pair to fully specify their behavior. To specify those programs, we can just conjoin multiple calls to evalo, and this is where the producer-consumer architecture becomes more apparent. Each evalo is essentially producing partial programs and sending them to the other evalos through this shared expression variable. With standard left-to-right conjunction, the first relation is going to produce a partial program and send it to the second relation, and so on. However, different input-output pairs may pertain to different parts of a synthesized program. If the first 9 examples produce a list term and the 10th produces a Boolean, then the synthesis has just spent all its time synthesizing a cons expression that it will ultimately have to throw out before replacing it with an if, per se, for instance, and resynthesizing the same expression. It would be better if, before synthesizing each sub-expression, each of these evalos could wait to see if some other evalo could bring its input-output information to bear on constraining the sub-expression before proceeding. And that's what Guarded Fresh is principally going to allow in this case. So what is Guarded Fresh actually doing? Let me preface this by saying that there is a large space of possible heuristics, both automatic and under programmer control, and this dependency information dependency information enables. I'm really just starting to explore this space, so what I'll describe here is the collection of heuristics that I've found so far to be the most helpful in program synthesis, and that I've tested in the evaluation section. So that said, consider the conso relation, which is a subrelation of evalo that synthesizes cons expressions. It accepts an expression, an environment, and an output value. The expression is unified with cons, and the output is unified with the cons pair, and then the car and cutter are evaluated in the same way. The broad intuition here is that we're going to want to see if expr and out are free, much like checking for the EOS symbol in the buffer example. If they're not, then we can evaluate the body immediately. If they are free, then we will want to suspend the body until we have more information about them, or until we run out of other goals to try first, in which case we'll just have to commit to their contents being new, free, unconstrained logic variables and proceed from there. The first thing that happens is that expr and out are unified with their respective patterns in the substitution. One minor optimization here involves the recognition that if expr and out are already bound, then there's no need to instantiate 4 new logic variables and extend the substitution 4 times. We can just look up expr and out and reuse their subterms in the body of the Guarded Fresh. I don't have good numbers yet on the contribution of each of these optimizations to the final performance, but just based on what I observed during development, I believe this optimization to be relatively minor, although worth the minimal effort to implement. Normally, Fresh would cause a delay that passed control to other branches of the search before evaluating its body. So another optimization heuristic I've been using is that if expr and out are both already ground, we just evaluate the body immediately. The intuition here is that we might as well just spend our computation cycles consuming ground information rather than speculatively unifying free variables with values that may later cause failures. We do have to be a little bit careful here because of a guard clause just unified a variable with a pattern, we don't want a subsequent guard clause to take that unification as important ground information, as it's not a constraint that is coming from outside the program, but just a unification that will be made in every execution of the program. Essentially, the way we distinguish between constraints on the top-level program variables and bindings created by guard clauses is to check whether any suspended goals depend on the relevant variables, because if they do, that means they must have unified those variables. It is possible to write perverse programs that infinitely loop with this heuristic, such as by trying to destructure the same ground term over and over again, but it's not clear whether this poses a problem in practice, and so far it has yet to come up. Continuing on, if expr and out are free, then we're going to suspend, or if either one is free, then we're going to suspend this goal. We do this by pushing it into a queue that I referred to in the paper as a schedule, and proceeding with the next goal. If we push this conso into the schedule, it'll look like this. A 3-tuple with the list of what I call external variables it is still waiting on, a list of internal variables, which are those that were generated by the actual pattern expressions in the guard clause, the new variables, and a closure that evaluates to the body goals. If out was ground because it was already part of the input-output data, for instance, only expr will be in the external variable list. Essentially, as long as there is potentially more information out there to constrain expr, we wait as long as possible for it to show up. Once the other input-output examples are added to the schedule, assuming there are multiple input-output pairs for the synthesis task, then we'll have multiple such tuples in the schedule, each with different lambdas, or closures rather. Now suppose we run out of goals while the schedule is still non-empty. Then we can just pick one from the schedule, and in this case, let's just for simplicity's sake, we'll pick the first one. Assume the schedule is a queue by default, because this is what miniKanren does. In that case, we are essentially committing to expr being filled with these logic variables. When we make that choice, we go from expr being technically bound in the substitution, which it was from the time we evaluated the first guarded fresh, to now committing to the idea that the value it is bound to represents the best state of our knowledge in this program about the constraints on expr. Now we can consider it bound even though we didn't before, and all the goals that depend on expr, like the other consos, will have empty external variable lists and be prioritized over anything else in the schedule. That is, in essence, how guarded fresh currently works. Push goals that depend on free variables into the schedule, prioritize them if those variables become bound. If they remain free, decide to commit to them and treat them as though they are bound. It is possible to imagine other heuristics that, for instance, prioritize goals with fewer dependencies, or dependencies with more goals depending on them, or letting the programmer specify some combination of these strategies. One particular dimension that may be useful to give the programmer control over is that of the default order for removing items from the schedule lacking any more specific dependency information, because that has pretty sizable implications for the overall shape of the search. So I said we should use a queue by default, because that's what miniKanren does. And that will make conjunctions basically fair, in the sense that every conjunct will eventually be visited, and miniKanren won't diverge unnecessarily, as it sometimes does with conventional left-to-right conjunction. And there's been recent work on the properties of this type of fairish conjunctive strategies that explore its properties in more detail than I do in this paper. Conversely, if we used a stack, we would get something that more closely resembles a left-to-right conjunction. It can diverge, but it also better respects the programmer's goal ordering, which may be useful in some cases. In any case, let's look at how these heuristics hold up in practice. So I tested this implementation against another interpreter built with more traditional fresh on a few instances of 3 kinds of functions. The first was Boolean functions, because they require more examples to fully specify than some of the other functions. And I thought that would test whether guarded fresh could make better use of the later examples earlier in the process. Next were recursive functions of lists, because synthesizing a recursive step exhibits an interesting kind of data flow from the partial function to the arguments to the recursive call that are hard to anticipate in a static fashion. And finally quines, which are a common point of reference in other work on synthesis, and of course exhibit very unusual synthesis properties due to being both program and output. And as you can see, while AND was simple enough that both interpreters synthesized it fairly quickly, the slightly more complicated XOR was much easier for the guarded interpreter. Likewise, with all of the recursive functions, the one surprise was that actually quines were very significantly slower in the guarded interpreter. I don't really have a great theory as to why. It is true that quines, unlike other program synthesis tasks, only require one call to eval, and the guarded clause is primarily useful in cases where there are multiple relations that share some common variable, like expr across all the different input-output pairs, because it allows those relations that share a variable to interleave in complicated ways. So I predicted the guarded clauses wouldn't help, but I don't know why they seem to hurt so significantly. But at any rate, it does underscore the point that giving the programmer control over which heuristics to apply is probably the safest decision at this point. I'll also note that I tried an interpreter with the fair conjunctions I described that made no use of the dependency information in order to test whether the dependency information itself was helping rather than just the underlying fairness of the search. And it actually was enormously worse than either of the other interpreters. And I suspect that's because it spent a lot of time exploring paths that were really unconstrained and didn't get help either from the dependencies or from the programmer ordering of clauses. So finally, just to close, I'd like to make a remark about the type of problem that Guarded Fresh was actually ultimately created to solve, and it wasn't synthesis per se. Synthesis, at least when there are multiple evaluos, exhibits that producer-consumer structure where relations that share a variable through which they communicate may benefit from being interleaved. But writing a relation that manually interleaves parallel calls to evaluate would be very complicated. This structure shows up in other places, just I know there was some recent work roping together a parser and interpreter that found that the dependencies between the relations were complex, but it would be very difficult to write a combined parser-interpreter relation. So using the dependency reordering, it could potentially be possible to essentially automate the creation of that more complex interleaved relation, while still writing the human-understandable multi-relation version. But the use case I'm interested in particular focuses on semantic parsing, where you have a natural language grammar parser relation linked to some kind of semantic reasoning or planning relation, and you may want to interleave constraints from the grammar and from the semantic representation to narrow the search. So that's the real point, at least in my work, of these Guarded Fresh goals, and may give you a sense of the kinds of problems they might apply to you. And it's what I'm working on currently, so perhaps more on that in the future as it develops. Thank you.